Hello AP Chemistry and welcome to 17.3, which is, ding ding ding, the last of the discussions for chapter 17. Thank goodness, huh? Alright, so titrations using indicators. Obviously we can use a pH meter. That is lovely, and a pH meter is the only way we can actually get a titration curve, right? Because we need to know the pH that corresponds to all of my volume additions, right? But if we were just shooting for the equivalence point, right, like we did back in chapter 4 when we did our initial foray into titrations, an indicator can get the job done. As long as we choose an indicator that will change color along this steep rise. Okay, so again, that steep rise only accounts for approximately, right, we're talking far less than 1 milliliter, right, something on the order of a tenth, maybe 2/10 of a milliliter, right? But that rise, an indicator that changes color somewhere along that rise will work, right? And we see that for this strong base, strong acid titration, right? Rise is from about 11 to say 3. So anything that changes color in that window will be fine, right? Obviously, like we've talked about previously, when we talk about weak acids or weak bases, right, that window gets smaller and our choice of indicator has to be more thoughtful, right? Whereas both indicators here, phenolphthalein and methyl red, are appropriate for strong acid, strong base titration, right? The methyl red would be not useful for this weak acids titration because it changes color before we get to the equivalence point, right? And again, where the endpoint is the place where the indicator changes color, which in the ideal scenario is also the place that is the equivalence point, right? Likewise, if we were to flip that around, right, so again, both of these are good here, but if we were doing a weak base titration, right, only methyl red would work, right, and phenolphthalein would be insufficient, right? Okay, so a little bit more about indicators. So this figure is actually from chapter 16, where it first introduced the concept of an indicator to measure pH, right? Here are some pKa's of some acid indicators, right? So here we have methyl red, right, which has a pKa of 5.1. Now, typically, the useful range, right, is plus or minus 1 unit approximately, right, from the pKa, right? And ideally, the pKa should be closest to where we want, to where the equivalence point is going to be, right? So pKa of 5.1, and you'll see that approximately at 5, that's when it's the bright orange color, right, which would indicate somewhere in between the yellow and the bright red. Yes, somewhere in between the yellow and the red, right, is where we get orange, where again, orange would represent approximately 50-50, right, of the orange, of the yellow, and the red, right? Now, all of that should sound really, really familiar because all of that is the same language and the same thought process that happens when we do a titration of a weak acid, right? Because it turns out, right, all of our indicators are weak acids. That's why they have pKa's, right? They are all in and of themselves weak acids, which is why when we do a titration, how much we add matters, right? We are only adding tiny, tiny amounts, right? Usually a couple of drops, right? And it's a pretty dilute solution to begin with, and then we're only adding a couple of drops to our entire reaction vessel, right? Because they are in and of themselves acids, weak acids, right? Which means that we have a deprotonated version versus a protonated version. Right, so if we were to think about a quick titration curve here, right, like something here, and then like this, right, so if we think about this as our pH equals pKa point, right, our half equivalence point, right, that is what this represents, yes, that's the half equivalence point for methyl red, but we need that the half equivalence point of methyl red needs to overlap with, the equivalence point of the titration we're doing. Yes, does that make sense, right? In that we are actually layering on, we are taking advantage of the fact that indicators are acids to then, right, use it in something else, right, to give us information about another acid, right? Which is why it's all, right, so very cool how it all layers on top of each other, right? Same thing with bromo blue, right? If we're taking a look here, right, so bromo blue, pKa of 7, right, and we'll see 7 is where we get that 50-50 color, right, because again, that's approximately the half equivalence point, right, which then would overlap with the actual equivalence point of a titration. Yes, does that make sense? All right, all of this is awesome and fantastic, and thank you for listening, be good, and I'll see you soon. Bye.